Brilliant, thank you, Anne. So, welcome everyone to this AtlantOS Ocean Hour. My name's Christine Sams. I'm based in the UK at the National Oceanography Centre, and I'm a member of the AtlantOS steering group. So on the panel, we've also got Mariana here today, who's coordinating everything and keeping us all in check. Thank you very much. And a whole panel of speakers today who will get around to introductions as you speak. I think that's what we'll do. So just to set context, AtlantOS isn't a program now, so it was an EU project, now a program, and it's really focused on advancing sustained ocean observations around the whole Atlantic basin. So it's a kind of collaborative, cooperative partnership. And we're trying to encourage engagement from all those countries around the basin to kind of work together, thinking about how we share data, information systems, lessons learned, things like that. And that's what this event is part of. So we have this webinar series running with an event every other month. And we're always interested in hearing ideas of speakers or topics that you think would be really relevant to you. Yeah, so today, well, I will not waste any more time. I was going to say one thing actually. So we've got 5 great speakers attending. We have got a bit of a North focus today, which is unintentional, but I think it's going to be really fascinating and great group of people. But, you know, obviously really keen to encourage speakers from other countries around the basin. So shall we just jump in and get going? So the first talk, we have got Samantha Wills talking about sail drones. Okay.
All right, just getting my screen set up here. Are you seeing my screen okay?
Yes.
Yep.
And just to say, I'll keep track of time and I'll give you, yeah, when we're close to time, I can give you a note.
Sure, let me know because I can't actually see. So maybe you just want to jump in and give me a 1-minute warning. So,
okay.
Thank you for having me here today. My name is Samantha Wills. I am at the University of Washington and NOAA at the Cooperative Institute for Climate, Ocean, and Ecosystem Studies. And given that this is an AtlantOS meeting, I thought we would talk about the tropical Pacific, where I have used sail drones, but of course, these are used throughout all of the ocean basins, and just wanted to kind of share some of the use cases that we've had and introduce you a little bit more to this observing technology. So Saildrone is a third-party company that we partner with to pretty much lease their drones for certain periods of time for missions. And they have 3 different types, at least that I'm aware of. The Explorer, which is the one that I will be presenting on today that we have personally used, which is a wind and solar powered drone with the, the goal there that you don't have a motor disrupting the air-sea interface where what you're trying to observe. And they have pretty great endurance. We've had missions where they've been out for 8 months almost at a time, if not a year actually, on one of them. And these are the smaller of all of the 3 drones here. The 23 feet or 7 meters long compared to the Voyager and the Surveyor, which is up to 20 meters long. And the difference with those 2 here on the right are that they both have diesel and electric power, which gives you that advantage, I think, if you're stuck in conditions where you need a little boost to move. But there's certainly, trade-offs because, of course, the price goes up the bigger the drone you get. And so for now, we have been looking at so much at this Explorer drone. And so here's a quick little schematic. You can see in the bottom left a little human figure there with respect to the size of the drone. So they're definitely autonomous. They're not meant to have any human crew on board, and they're remotely piloted by sail drone engineers. And here it just kind of gives you a quick overview you can look at later where all of the different sensors, both kind of a combination of oceanic, atmospheric, and biogeochemical measurements, in addition to other sensors we put on there, such as long wave solar radiation, and other instruments that we might be able to attach to the hull, for example. So that's just kind of if you want to look at this later, if you're curious, this gives you some senses. But one key part here is that the measurements we can collect are very high resolution. We're able to collect 1-minute samples as we, go on a trajectory throughout the ocean. And so it's really giving you this very good look into the smaller spatial scales and time scales of variability. So with my project, we have been primarily in the Eastern and Central Tropical Pacific as part of this initiative for the Tropical Pacific Observing System, which here shown in the white squares are the Tropical Atmosphere Ocean Array buoys. And you can see here in the black all of the different paths we've taken since 2017. We've had 5 missions total so far to the Tropical Pacific. Half of them have left out of Alameda, California. Others have left out of Honolulu, Hawaii, depending on the study region that you're trying to get. And the goal for us has mainly to be to get down to the equator. But it's kind of cool because you don't necessarily have to worry about getting a big ship deployment and getting out into position and getting a whole crew out. And so it gives us that advantage and that flexibility. But at the same time, there are some drawbacks to the drones where we've tried to keep them in formation together, but unfortunately, given that there's solar power and wind power, when you have low wind speeds in the tropics, as you typically do, and high ocean current conditions, you can certainly have a reduced efficiency in navigation, and sometimes the currents can overpower the drones, and we've had instances where they've drifted off towards the west with the currents, especially during the fall season. But at the same time, the advantage of having these multiple drones out in the ocean together allows you to sample both time and space scales simultaneously, and especially capturing subgrid and subpixel variability. This here is from a case study where we were looking at atmospheric cold pools, which if you've ever been on a ship or outside and there's a storm in the distance, and then you feel that rush of air go past you, that's a cold pool that you're feeling. And so with the ability to measure temperature changes on minute timescales, we're able to capture these rapid scales of variability and also get an understanding somewhat of the spatial grid that is not necessarily captured by satellite products, reanalysis products. And it really just gives us this advantage to look at sort of a 2D space and not where you have both time and space together. And so here's an example too of a different cold pool where within a 0.25 by 0.3 degree grid space, we had 4 drones and 1 tow mooring. And this white vector here is the single point of the ERA 5 analysis that's available for this grid box. And you can see here in the arrows that we had 4 different drones plus the tow mooring capturing the changes to the environment as this cold pool moved through the region in just a 20-minute period. And so with the iMerge precipitation product being about 0.1 degrees, we can kind of see the imprint within the pixels here of the cold pool that's captured by the in situ measurements, as well as here the corresponding time series and the temperature front, as well as the gust front associated with this expanding cold pool. And so it's kind of interesting because you can really begin to get a sense of the timing of intercept at different locations, as well as giving you a sense of the strength as it's moving across the area, if there's any sort of dissipation or not. And so this really gave me this idea that coming from a traditionally land-based atmospheric scientist, it got me kind of thinking about the land-based mesonet that we have. So this is the state of Oklahoma in the United States. And this here and all of these little yellow dots are observing stations placed throughout all of the counties in the state. And they're able to get out mesoscale features such as this low pressure system that came across the state here in 1993 in this figure here. And the idea being that you can capture these mesoscale phenomena spanning hundreds of kilometers or less on minutes to hours, so long as you have enough observing platforms within a certain area of each other. And so given that this is on land, of course, you know, the drones give us the ability to actually implement a similar type of mesoscale network or mesonet over the ocean.
Samantha, so here what I have 7 minutes. Sorry, 7 minutes.
Yeah. Okay, well, then I'll finish up here on this slide. So if you wanted to imagine perhaps having the state of Oklahoma with respect to the tau and the Parada arrays, and in considering the scales of variability that you might be capturing that's lost in these larger scale arrays. And since I'm over, I'll leave it at that. So I end the show.
Brilliant. Yeah, thank you so much. What a shame to cut you off. That's horrible.
Sorry, no, I had one last slide. You're totally fine.
So I should have said beforehand that please put questions in chat if you've got questions, and if they're for a specific person, then please make that note as well, and we'll put questions to the panelists at the end of the talk, right, rather than in between. So if I may skip straight on to Dong Zhao, are you ready to take over? Please introduce yourselves. Sorry, I'm going to let you do it and get your names right. And
okay.
I think Samantha has to stop unsharing. So thank you.
Do you see my screen? Maybe not.
Not yet.
Oh. Oh, sorry, ask for my permission, so I need to change all the settings.
Maybe another speaker can go, or do you think you can?
Yeah, now do you see my screen now?
Now, yes.
Yeah.
Okay,
Yes.
so I have to find my presentation though. Sorry about that.
That looks good.
Is this good now?
Looks like it's
Almost. Yes.
Okay, good. Oh, hi everyone. I will just provide a quick introduction to the USV cell drones for hurricane observation. Over the past 2 decades, hurricane track prediction has dramatically improved, while the improvement in hurricane intensity forecast has been lagging. The lack of direct measurements at the air-sea interface inside the hurricane has been recognized as the roadblock, since the rapid intensification depends more critically on the internal dynamics and thermodynamics of the storm. The sea states, like the one pictured here, prevent us from sending research vessels into the storm for measurement. We'd like to test if we can send USV cell drones to do the job. The hurricane or extreme weather cell drone was developed from the conventional cell drones that have demonstrated its capability in the tropical Pacific, as has been shown by Samantha, and the tropical Atlantic here during atomic Eureka 4A field campaign in winter 2020. During the campaign, one NOAA cell drone was dedicated to the trade wind alley, shuttle between the airplane service circle and the NTES buoy. The other NOAA cell drone sailed with 3 NASA-funded cell drones in the ocean eddy corridor as a cluster to resolve the mesoscale submesoscale processes. The NOAA cell drones measure the wind stress and the full components of air-sea heat fluxes, and sailed close to Ron Brown and French vessel Atlanta, the NOAA weather buoy 41040 and the NTES buoy for intercomparison. They also extended the atomic observation from winter to summer to cover the peak season of Amazon River outflow and the seasonal migration of the trade wind. The upper middle map shows the track of one cell drone in April crossing ocean eddies. April is the peak season of Amazon River outflow reaching this area. The lower figures show that the extreme of salinity front are associated with ocean eddies and strong currents. The total distance traveled by the 2 NOAA cell drones logged over 23,000 nautical miles. However, the test experience of regular cell drones in the Northern Ocean winter and the Southern Ocean has not been pleasant. The damage shown in the upper right was a result of a test in the Southern Ocean. The solution for severe weather conditions is thus a shorter and strengthened wind and sensor mounts, but can the slower speed due to the shorter wind even be viable for hurricane observation, since hurricanes move and they can be faster than sail drone speed? The 2021 hurricane season brought us the first test. 5 sail drones were launched, 3 from St. Thomas, 2 from Jacksonville, Florida. They sail to the designated areas which have high probability of experiencing tropical storm winds based on the 20-year climatology. The probability is shown here in color in the left figure, along with the tracks of tropical cyclones in the past 20 years. The 3 sail drones in the red polygon were following underwater gliders to collect co-located measurements. All sail drones were mobilized to intercept track when the hurricanes or tropical cyclones were predicted. 2021 was a busy season. The sail drone intercepted 5 tropical storms and 1 Category 4 Hurricane Sam by sail drone SD-1045. Henry also developed into a hurricane after passing sail drone SD-1031. The pink lines were the underwater glider tracks. The black dots here, you see, were coordinated airborne measurements, including drop zones. In 2022 hurricane season, 2 more sail drones were deployed in the Gulf of Mexico. The 7 sail drones sailed to the 7 blue rectangle areas. 5 of them were following underwater gliders shown by the gray tracks when no hurricanes were in development. The 2022 season was a quiet season, started with no tropical cyclone development at all in the first half of the season until mid-September. Then 2 major hurricanes, Fiona and Ian, formed. The lower left shows the tropical storm and hurricane force wind of Ian along its track. The sudden change of predicted path devastated the Southwest Florida community, also diminished the hope of sail drone 1032 to intercept the track. The SD-1059, on the other hand, caused the re-intensification of Ian back to Category 1 hurricane after it passed over Florida. This re-intensification was not well predicted. The sail drone measurements were therefore used by the National Hurricane Center for the verification in their advisory. The lower right figure shows the tropical storm and hurricane strength wind along Fiona's track. 4 sail drones were in line and measured the different stages from a tropical storm to Category 4 hurricane. The 12-day sail drone tracks were shown in blue along Fiona, with the stars indicating the location of the 4 sail drones closest to the storm center. All sail drones were actively engaged in pursuing Fiona. The SD-1083 was able to sail into the storm with only a few days of action time. SD-1040 left the underwater glider that it was following to sail to Fiona here. SD-1031 was likely near the center of the storm when it was intensified into a hurricane, while its SD-1017A was the one sailed into the eye wall and sustained some damage, unfortunately. The sequence of development measured by the sail drones will be interesting to investigate when we receive all the data back. So the last slide showing a video captured by sail drone 1045 inside the eye wall of Hurricane Sam, the Category 4 hurricane. So in summary, USV sail drones have demonstrated their capability as a viable hurricane observation platform. That's all from me. Thank you.
Thanks very much. Wow, what an incredible video. And what a really good use of autonomy. So I certainly wouldn't want to be anywhere near there. So let's pass over. So our next speaker, I'm going to jump straight across to Bastian, but please don't forget your questions. So if you've got questions, put them in the chat and don't forget them as you listen to everybody else's introductions. So yeah, I think you need to stop sharing. No, I don't want to stop that video either.
Let me find the...
All right, let me start up the video share. So
very efficient, brilliant.
Thanks very much for having me here. It's a great pleasure. So I'll be presenting some work that we've been doing in the Arabian Sea, trying to constrain the processes that cause ventilation of the Arabian Sea oxygen minimum zone. So my name is Bastian Kest. I'm at the University of Gothenburg. And I'll also be presenting, this is not all my work. A lot of what I'll be showing has been done by Estelle Font, my PhD student. And we've had lots of contributions from the Polar Gliders group also at the university, and obviously a lot of support from our partners in Oman, Sultan Qaboos University. So first, a little bit of background. Why do we care about the oxygen minimum zone? For those who might not be acquainted, oxygen minimum zones are deep layers in the ocean, generally from 100 to 1,000 meters, with very low oxygen. So this has big implications for habitat space, but also biogeochemical cycling. Now, recently we've started to realize that actually we have no idea what's going to happen to them. So if you look at CMIP6 models, this is what we're seeing in the second figure. This is the mean trend amongst all of the models of the oxygen minimum zones. So I don't actually want you to focus on the colors which represent the trend. I want you to look at the stippling, the little dots. Where you have dots means we have certainty. You notice that we have no dots in the oxygen minimum zones. Now, the criteria for certainty here is 80% of the models need to agree on the direction, not even a question of magnitude, just direction. This just highlights how little certainty we have on how these oxygen minimum zones are going to evolve. And this happens because they're very complex ecosystems. Oxygen minimum zones exist because there is more oxygen going out than there is going in at its most basic. But if you break it down, you can look at different components. So for example, the total budget here in black in the equation is composed of advective transport. This is in blue. And then mixing processes, which may also ventilate in red. And then finally, biological processes. So respiration within the oxygen minimum zone, which creates an oxygen demand. Now, all of these processes have really complex feedbacks and interplays, often opposing each other. So stratification will prevent ventilation, but also prevent production, which limits oxygen demand at depth. So to really understand what's happening, we need to go in there and figure it out at a grid scale that's smaller than what the models can resolve at the moment. And so an ideal tool for this is gliders. So hopefully most of you are acquainted with gliders, but for those who aren't, gliders are autonomous underwater vehicles which profile the water column from the surface down to generally 1,000 meters going up and down. And they do this by changing their density by either inflating or deflating a bladder. This changes the volume, keeps the same mass, they float or sink. And then they point their nose in the right direction, and this means they move in a sawtooth. So they're able to do about 20 kilometers a day. And while they do that, they're able to measure many parameters from very flexible payloads. Our gliders measure at 16 hertz vertically. So you're getting millimeter scale, 5 millimeter resolution in temperature and salinity, for example. And then when they come to the surface, they send all of this data back via satellite. And so we're able to see these beautiful curtains of data that start to appear through the ocean. And the beauty here is because they don't have propellers, they have long endurance, but they also have high resolution. So this allows us to capture not only the mean state of systems, but also the extremes, and especially do this where it might be harder to go with a vessel. So the Arabian Sea has been a great example for this. It's a data poor region, and the gliders have really increased the number of observations that we have in the region. So thinking back to the oxygen minimum zones, the most obvious source of oxygen to the deep is the atmosphere, the biggest reservoir for oxygen. So one of the main things that we wanted to constrain was actually the dynamics of the surface layer. So this is a recent paper by Estelle, which was trying to look at the variability of the surface mix layer, which is able to control some of that vertical flux. So we first determined a heat budget, total heat flux, which is what we generally consider to be the primary control on the surface mix layer depth. But at the same time, we also started looking at these sub-mesoscale processes. So these are processes that are order of hundreds of meters to a few kilometers, which are also responsible for a lot of changes in mixed layer depth. Specifically, we focused on two of them, mixed layer eddies, which are the conversion of fronts, so lateral gradients, into vertical gradients, so stratification through ageostrophic breakdown. And then Ekman buoyancy flux, which is another slightly complicated phenomenon, where if you have a front and the wind blows along the front, the Ekman flux will actually transport water from one side to the other. So if you have dense water going over lighter water, it will convect. And the opposite, if you have lighter water going on top of dense water, it will re-stratify. And so we were able to do these equivalent budgets. And we identified that actually these sub-mesoscale processes, particularly the mixed layer eddies, are responsible for 68% of the positive buoyancy flux in the winter. This means that these tiny kilometer scale processes are incredibly important for strengthening the stratification in the winter when mixed layer depth is deepest and coupling between the atmosphere and the oxygen minimum zone is strongest. So they really inhibit vertical fluxes of nutrients and vertical fluxes of oxygen. Now, the region is also very interesting. It's very complex because we have a number of water masses in the area. So on the left here, we have vertical views. You have depth on the y-axis, latitude on the x-axis. So these are 60-kilometer sections, two of them at different times of the year in the same location. And these two bottom panels here show oxygen. So in blue, you have absence of oxygen, the oxygen minimum zone. And what I want to draw your attention to is this layer between 200 and 400 meters, where we have dramatic changes in the oxygen concentrations. And you can see that this is directly linked actually to the amount of salt in the water. And this is because we have this Persian Gulf water, which flows out of the Persian Gulf along the shelf edge, and it gets sheared and distributed by these large and small eddies, which bring oxygen and spread it around the Gulf. So this really has a big impact on the depth of the oxycline. Now, the main thing I want to draw attention to is these little patches over here. These are very small. They're order of 5 kilometers. This is much smaller than what most regional models resolve and what gliders even can resolve a lot of the time, because dive spacing is generally about 4 kilometers. And most importantly, if we want to understand fluxes in transport, we can't do it the traditional ways here because geostrophic approximations simply don't work at these scales. So we've gone back out there, and this is work that we're doing at the moment with a glider that's equipped with an ADCP. And we've been collecting this 9 months time series of ocean currents at very fine scale, 2-meter resolution vertically. So you see the currents here along slope on the top, and then the oxygen concentrations below. And we're starting to look at the coupling of these two and what the fluxes in transport are of oxygen. And what we can really see is if we zoom in on sections are these small eddies.
Question 7 minutes, just to give an update. This is the
last slide, cool. Which are responsible for a lot of transport of oxygen and also stimulating a lot of biology. So these are the key processes we're trying to resolve. These two are well on their way, 2 more that we're still trying to capture, and we've got a few remaining unknowns, the biology and trying to get direct measurements of mixing. Thankfully, we were just funded last week. Actually, we have a grant to go back and get these measurements of the biology and the mixing. So I will leave it with a cheeky advert. As a result, we'll be hiring a PhD student to do glider-based mixing and nutrient and oxygen fluxes. Thanks very much, and thanks to our funders.
Brilliant, and congratulations on the proposal.
Thanks, I'm
new
very
project.
excited.
So we've got 2 more speakers. We are going to skip across to Sunai next, talk about wave gliders.
Just give me 1 second. Does that look good to everyone?
Yep.
Great. So my name's Sunil Iyer. I'm currently a postdoctoral scholar at Oregon State University, and we'll be talking about work that I did as part of my PhD dissertation at the University of Washington. And I would like to acknowledge my collaborators, Elizabeth Thompson, Kyler Druschka, and Jim Thompson. So today I'll be discussing observations from 2 types of platforms deployed as part of the Atomic or Atlantic Trade Wind Ocean Atmosphere Mesoscale Interaction Campaign, which is the same campaign as Dong Xiao mentioned in one of the previous talks. So this took place in early 2020 to the northwestern tropical Atlantic, and the study area is denoted by the black box on that screen on a background of satellite sea surface temperature. And we can see that area, there's a lot of small scale structure, that is small scale SST variability. So considering that, our primary goal was to look at how such sub-mesoscale structures influence air-sea interaction and fluxes, and we did that using these platforms. So the first of them are wave gliders, which are a type of autonomous instrument that was originally developed and currently produced by Liquid Robotics. And the diagram on the bottom right illustrates a bit on how these work. They're solar powered and equipped with communication systems, so they can be remotely piloted. And they are, you can see there's that surface vehicle as well as a tethered submerged glider. And that tethered glider is equipped with a set of wings that feather back and forth with the motion of the waves. So they're using that wave orbital motion to propel themselves forward. And because waves are quite strong, they can move up to about 2 knots. So relatively quickly, and certainly a lot more quickly than ocean currents. The instrumentation itself consists of a suite of sensors to measure key parameters in the atmosphere and the ocean, including air temperature, humidity, ocean temperature, salinity, surface currents, and waves. We deployed wave gliders, 2 of them specifically for between 30 and 34 days during atomic, but I will note that wave gliders have the capability to stay out in the ocean for a lot longer than this. They can stay out for 6 months to a year, so could be used to look at larger scale features as well, or longer time variability. The second type of platform we deployed were surface wave instrument float with tracking, or swift drifters, which are a type of Lagrangian float that was developed by Jim Thompson's group at the Applied Physics Lab at the University of Washington. And I'm not going to say as much about these, but in short, they're wave following Lagrangian platforms, so they drift with the surface currents, and included instruments to make similar measurements that we get from the wave gliders. And we deployed those for a slightly shorter period of time, but like with the wave gliders, they can stay out for a lot longer than that. So the next slide shows a video of sea surface temperatures observed from both the swift drifters and wave gliders during the entirety of atomic. And the key point here is that we can observe a lot of these small scale features in situ. So if I play that, the ship will be the black dot, and the wave gliders being the diamonds, and the swift drifters being the X's. So if I play that, you can see those wave gliders appear to move relatively fast. Of course, this is sped up quite a lot, but they're traversing these SST or sea surface temperature fronts back and forth. On the other hand, the Lagrangian floats are a lot slower and don't have necessarily the same spatial coverage. So by using both types of these platforms, we can get an idea of a wide variety of different processes that are occurring, such as smaller scale spatial variability from those wave gliders, as well as maybe a bit larger scale features when comparing different swift drifters located across gradients. So I thought I would end by saying, by zooming in on one of those small scale features to show some of the patterns that we can observe from these instruments. The plot on the right is a map of sea surface temperature from the 2 wave gliders during a 4-day period between the 2nd and 6th of February of 2020, while the plot on the left shows these observed sea surface temperatures as a function of distance from that frontal boundary denoted in black on the map. And the idea here is that we can see that SST increases quite a bit going west to east across this front. In other words, we observe a lot of persistent spatial variability here. However, because wave gliders made a bunch more measurements than just SST, we can also calculate bulk air-sea fluxes using using these observations. So that is what's shown in the bottom left plot, specifically sensible heat flux in this case. And we see that, like with SST, sensible heat flux increases going from west to east by about 4 watts per square meter. So the idea here is that these small scale ocean features play some role in modulating air-sea interaction in this region. So that's all I have. I'd also like to acknowledge the NOAA Climate Program Office as a source of funding. And for those of you interested, we have published a couple of papers based on this work. So please check those out. Thanks.
Thank you very much. Super, really exciting data. So our final speaker today is Shep Smith from X-Ocean. And then we'll get to some chat.
All right, can you all hear me?
Yes.
And I hope that you're now seeing my screen.
Yes, absolutely.
Great, thank you. So quick introduction, I'm Shep Smith. I was with NOAA for 28 years in the Commissioned Officer Corps. I finished as the director of the Office of Coast Survey. Took a year off and hiked the Appalachian Trail, went back to work. I took a year off after retiring, went back to work as the Chief Technology Officer for X-Ocean. So X-Ocean is an Irish-based company, Republic of Ireland, where we design, build, and operate a fleet of uncrewed surface vessels, mostly for offshore surveying. So I'll introduce you a little bit to it. I wish that I had a really good sort of science project example to share, because that's the style of these presentations. But I'll touch on a few of the projects that we've done along the way. So we've got our main facility is in Ireland. We have the largest fleet of survey class USVs. So these vessels are precisely navigated. They're have 2 thrusters, diesel, electric, and we can be wherever we need to be within less than a meter through really good positioning and autopilot systems. We've built 25 of them so far. We're building about a new one every month. And have global experience. We've had 70,000 hours of system operation and operated in over 18 countries. I'll tell you just a little bit about how it works. Obviously, like the other examples of USVs, there's nobody on board. We have a connection to a cloud-based what we call the cyber deck, the whole control system for the fleet, and have our pilots and surveyors remote in through that system. Because we work in coastal areas, we operate in a regulated environment, and the regulators really expect us to have one pilot for one boat operating all the time. So we have a watch that's continuously there, talking to other vessels on VHF and doing a lot of the things that a normal vessel would do. You see a lot of the pictures are in wind farms. About 80% of our work is for offshore wind, for either the first level of mapping to plan out the installation, or some of the O&M work, monitoring things, monitoring the cables and the foundations and that sort of thing. But we have also done some habitat work in that context with fisheries sonars and other work, and I'll talk a little bit about some of the projects we have coming up as well. From there, we have the cloud-based data processing system for all of the seabed data, where we work on that data. Again, it's a cloud-based system, so our people are all over the world working on sort of a shift basis on analyzing the data and making it, turning it into something more meaningful. Right now that our data rates are high enough that we have to wait for the boat to get back to get most of the data off. We have enough that we can see that the data is good, but not to be able to interpret it in full resolution in real time. But we do have Starlink systems are being installed right now, and for many applications, we think we'll be able to have real time access to the full resolution data, which will open up a whole new suite of opportunities for near real-time mission planning, adaptive mission planning. So what this is, fairly typical suite for this type of survey work. We starting from the bottom, we have sub-bottom profilers that we can obviously see through the seabed in order to understand the structure, particularly in support of cable routes or foundations for wind farms. The bathymetry itself at a very high resolution, obviously it scales with depth for a surface vessel, but also the backscatter. One of the things that I think is really exciting about these boats is that we install these systems, they stay on there. We can install them, in the shop and very carefully. Everything is really tightly calibrated, and the data that comes off is really beautiful. And so we're really pleased, and our customers are very pleased with that as well. Seabed features, interpreted seabed features. Water column. There's a lot of information from the water column itself, from the backscatter, from the multi-beam systems that for the most part, goes unanalyzed and unvalued. I was the CEO of the NOAA ship Thomas Jefferson during Deepwater Horizon a few years ago, and I was amazed when we started looking more carefully at the water column, at what was available to be interpreted out of there, not only for biological things, but physical processes and internal waves breaking and all kinds of fun stuff. And then we have a typical MetOcean data suite on the surface as well. So going forward, we've concentrated on everything we can do from the boat itself, but there are a lot of applications where we need to get the sensors down in the water column, and so we're developing a towed system. The first application for that will be normal sort of geophysical work, side scan, etc., magnetometer, But going forward, we're also looking at a variant of the same fish using the same cable and control system and everything that would have an eDNA sensor, a fluorometer, CTD, et cetera, in the fish, and then a complementary suite of sensors on the boat to go with it for fisheries and habitat work. And again, a lot of our customers are interested in wind farm work. There's a lot of questions, including a paper I just saw came out today on the habitat implications of wind farms that I think is not fully understood yet, and we're going to need a full suite of observations like this to be able to understand that. In addition, we have a few applications for UAVs off of using the drone itself as the platform to send up a flying drone for marine mammal observations, maybe inspections of the wind farms themselves. We do some shoreline mapping, although that's usually easier to do from the shore than it is from the boat. And then AUV deployed from the vessel as well. So there's over the next few years, we're going to have a whole suite of more sensor opportunities that I think will be more broadly available for science applications. And that is it.
Thank you. Perfect timing. I was just going to say 7 minutes. You're good.
All right.
Thank you.
Following instructions,
Thank you so much for the amazing talks. Thank you for all the speakers for the talks. So now we have some time for questions. There has been a lot of questions already in the Q&A, like people directed questions to the specific speakers, but also it's an open floor. So anyone can, if you want to, unmute yourself and ask a question, feel free.
If not, then can I jump in with one just to get going? So we've heard about some really fabulous technologies there, really changing what we can do in terms of science and what questions we can ask and what we can expect from the data. So I'm interested just to hear from different members of the panel, if you've got ideas about how can we maximize the benefit of these technologies, how do we, make sure science can access and make sure it's more kind of accessible maybe to other groups of scientists, right? We are very northern focused here. So just throw that out and see if you've got any ideas. I don't know where to start. Should I direct? Well, or do you want to just unmute and start talking? I don't know.
So from my perspective, there's two things. One, there's reusability of the data, making that accessible. And I think there's a number of initiatives already on this front. You know, most autonomous vehicle data goes out via GTS and is available for operational models. I think the other question is availability of the platforms. A lot of science groups have the platforms, do an experiment and have it sit on the shelf. And in Europe, for example, there's the GROOM2 project, which is trying to build a European infrastructure where actually you're able to leverage different groups, platforms or pilots and everything. And I think that's probably a really good way forward to make this platform more accessible to everyone, or at least a lower barrier of entry.
Yeah, interesting to see if we can do it outside national boundaries or outside the EU.
Little steps.
Anybody else want to jump in there?
Yeah, the Cell-Drone business model is a little bit different than most of the other platforms. It's a paid for service. You pay for the data you get. So there's basically no barrier whatsoever to anybody. Anybody can contact the company to get access to the service. But I would recommend, the data quality is the issue here. As with any ocean observations, even with ourselves from federal labs and universities, the data QC is going to be taken care of. The Cell-Drone company have done the first level, the level 0, I would say 0.5 data QC, but really the scientists need to take care of the data and share the data with the community. The other thought I have is that it's really critical to coordinate with other platforms. We have seen different kinds of uncrewed systems, including on the water and the surface. The advantage of those uncrewed systems are that they can be adaptive. They can be controlled in real time, both ways. So our standard practice is that whenever we have the possibility, opportunity, we always get together with other platforms, whether it's ships or moored buoys, for a number of reasons. One is to check the data quality. The other is that's really the two-way, not only for the uncrewed system, but also for the moored platform or ship measurements, because each one of them have their limitations, have their advantages, but also for better science, for the mesoscale variabilities. Thanks.
Thank you. Anybody else want to jump in? I was thinking, Shep, about the fact that a lot of your data that you acquire must be commercially sensitive. I suppose I was listening to you thinking, I wonder how the scientists are going to get their hands on some of that stuff.
Indeed. And this is I from my old days with NOAA and as a big champion for Seabed 2030, all about open data sharing. And now I find myself in a world where it does have commercial sensitivity. And I think there's a way through that to be able to extract data that is scientifically valuable, that has very little commercial risk attached to it. But there's a certain amount of congregating we need to do to get that vision in place to be able to do it. But I think it's really exciting as well, and some big opportunities.
So I'm gonna I will shut up. I'm gonna have one more question, and then please other people jump in. But I'm really interested in the science kind of technology interface then, right? How when does that work? When does that not work? What are the challenges between those two communities? I am sure from where I sit, that dialogue could be improved. So I'm kind of interested to hear if there's experiences of where that's worked really well, or where you see specific challenges or opportunities around that kind of interface. To anyone. Or not? Or is it all working brilliantly? Does it work brilliantly?
For us, it's actually working brilliantly. I've been really lucky to fall in a place where we have a foundation near us that also works with these platforms. And the mix of university, foundation, and industry, we've been able to do a lot of development and really push the platforms. So it's been working great for us.
So that's geographic. That's a geographic kind of.
There's a mix of geographic and the fact that foundations have different limitations to the rest of us mere mortals.
Any other different experiences or different perspectives?
Sorry, could you just rephrase the question you had?
So I suppose what we've heard is we've got technology providers here. We've also got scientists who are just working with the data. And I think in terms of the fact that a lot of these technologies are quite innovative, a lot of them are still under development, how the science community and the technology development community interact is where I'm interested, where that, does it work well? Could we learn lessons from where it's working well in other places and, share those? So I'm kind of just interested in that interface.
Well, I guess I can elaborate a little bit, and Dongzhao, please jump in here. At least with Saildrone and them being kind of an independent company that we use their technology, we do have a pretty good two-way communication, I would say, with their engineers in order to express if there's perhaps a new sort of sensor, because some of these have standard sensor packages and you might want an additional measurement that's not part of the standard suite of sensors. And so a lot of times, they have been willing to work with us in order to get that somehow implemented onto the platform itself. Although sometimes there's also pushback and difficulties. And I think too, one of the harder things with perhaps the private company is that they're not always, I think for the most part, everyone probably has some sort of science question, but they're not just limited to science. They can also take industry needs. And sometimes too, I wonder in terms of where the funding comes from, that can also sort of take away some of their interest perhaps in a more science question versus a more, financial transaction type of thing. So that's, I guess, one thing I've seen in terms of it not being completely in-house. You have a little less control over some of how you'd like it to work versus how it works.
Yeah, you answered well. I think for us, it works well. I think that's because of the mutual understanding between the science party and the commercial industry. Because they are commercial, right? Any change they make, they will depend on how much benefit they will get long term, and not for one small project. I guess this is the challenge when you don't have the full control. But again, the two-way communication, the mutual understanding will be the foundation of those kind of collaboration.
Makes a lot of sense. I can see quite a few questions in the chat. Should we jump there, Mariana?
Ajit also raised his hand. I'm not sure if I'm pronouncing your name right, but yes, I think you should be able to speak.
Yeah, thank you. I put the question in the chat, but just to sort of expand on that, Bastian has heard me sort of get on my soapbox about this, so I'll spare him that. The issue I see is in all the presentations, there is this issue of measuring doing measurements in relatively small scales. And it came through really well in Sunil's presentation, where when you saw the two platforms and they were overlapping, saw small changes in temperature, which I presume is happening because of the lack of synopticity. So I'm curious to hear from the panel how you're thinking about this issue of synopticity when you're deploying more than one platform at a time. How do we interpret the data? How do we think about it?
Yeah, so I agree. Yeah, the differences in temperature in my figures are between those platforms are due to time variability. And in terms of interpreting the data, if we're looking at like a wave glider moving along an SST front, of course, you might have to make some sort of assumption about temporal variability that over a short period of time that isn't a large factor. Another approach is to use like specific targeted strategies when deploying the instrument. So for example, we had the 2 wave gliders and we intentionally directed those to follow each other's tracks. So one wave glider was following the other, and doing that, we can get like simultaneous observations on either side of an interesting feature. And using that, we could limit the amount of variability that would be from time alone and just look at the spatial changes.
Do any of the other panelists deal with multiple measurements from instruments and how they think about trying to get at interpreting a synoptic signature?
Well, I think really the on-cruise system brings the hope to really take care of the synoptic measurements that you were saying, because as Samantha envisioned, the Mesonet type of network is possible now with a fleet of on-cruise systems to work together in a cluster to resolve the finer scale variability. Of course, it's the funding that's the issue that can support such activities. That's why coordination across different platforms will be the key for the future Mesonet network establishment. Not only, for example, not only the sail drones, a combination of sail drones, wave gliders, underwater gliders, even the aerial drones. That's the possibility. Yeah, in the very near future, I would say.
So I think like we have like, we're close to the top of the hour, but if the speakers could stay, there are a lot of questions in the chat. I think people might just be shy to raise their voice and talk, but if people could stay, maybe we could, yeah, or answer as a group, like the speakers can answer the questions loud or type in the chat. But as we're at the top of the hour, I just want to thank everybody for joining this Ocean Hour. And thank you, of course, to all the amazing speakers. Thank you so much. And the next Ocean Hour is going to be in January. So we're going to take a break for the holidays. Hope everybody have a great time during the holidays. And we're back in January. So keep a look for the emails and for the advertisement. And see you in the next Ocean Hour.
Thank you again to, yes, all the panelists. Really appreciate your efforts and attendance.
So yeah, we can keep the recording in, but I think we just, yeah, we're done. But there are a lot of questions. So I don't know if you guys want to respond like live so we can have that in the recording, or if you want to type, but there are a lot of questions coming. I think people might just be shy.
I saw a question about the wave measurements by sail drones. I can see that the comparison with the moored buoys, the NOAA weather buoys in the Western tropical Atlantic has shown excellent agreement between sail drone measurements in terms of significant wave height and wave period. We also have the capability in development to have the 2D wave spectrum, the directional wave spectrum, but we haven't compared with the other platforms yet. But basic wave measurements are excellent quality from the sail drone.
If people want to raise their hand and just ask, can go on. Johan, you said your chat was closed. Would you like to ask your question? Feel free to type or raise your hand.
It might be. I don't know if it's. Yeah. There was an interesting one here that I picked up. Samantha, it's coming your way. It says Samantha was just at the point. I don't know if you've already read
Hello.
this.
Can I? Am I audible, please?
Yep.
Cool.
Sure.
Hello?
Go on. Go on. Yes, we can hear you.
It's an excellent presentation. So I'm Raja Acharya, working in India Meteorological Department in India. So I just I have experience in Port Meteorological Officer for the last during my 30 years of service. I worked for 5 years as a Port Meteorological Officer. So as you know, that in the VOS ships, as a voluntary observing ships, we measure a lot of variables, surface variables, and ocean meteorological data. So if these high-tech systems are towed to a VOS ship, in future, will it give a huge amount of data as well as the surface, as well as the beneath the surface? So both can be compared and calibrated and give a lot of information about the ocean dynamics. Because as you know, the VOS ships are slowly decreasing actually. Am I clear?
Did you guys get the question?
If you could maybe rephrase, that would help.
Should I repeat? Hello?
If I understood correctly, the question was related to how we're going to manage to do the intercalibration between all of these autonomous platforms and what we've had traditionally as vessels doing surface observations. Was that right?
Yes, correct. Yes.
Yeah.
Right, sir.
I mean, from my perspective, as I use Gliders, so I'm not using surface platforms particularly, we still rely very much on the ship. So we do our calibration in the lab, and then we do our calibration in the field. And we are hugely dependent on that. But I don't know about you guys for surface platforms, what your experience has been.
I can jump in. Oh, sorry, I didn't want to interrupt you.
Okay, thank you. A lot of things actually. Actually, I have come across various papers. They actually suggest about towing of certain platforms to some ships actually, so that actually they make a combined observation from various platforms actually. That's why I was interested to make this queries actually. Thank you very much.
Thanks.
Thank you. I think maybe we can stop the recording. And I think like if you guys want to respond in the chat, it seems that the people might be shy to ask their questions directly. I also don't want to hold you guys. So the ocean hour is 1 hour. So the speakers, if you have to leave, feel free to do so. And maybe people can follow up by emails if you guys are okay giving your contact information. People can maybe contact you by email. But I'm also happy to be here and